What up, fam? Let's get going on this AP Stats Chapter 5 review. So when two coins are crossed, the probability of getting two heads is 0.25. This means that. So without looking at the answer, we're looking at this word probability. Anytime you're looking at the word probability, you're trying to be thinking about something in the long run, is what they're going to be saying. In the long run. You may have also used other terms such as the law of large numbers, or when you've done something a whole bunch of times. So you've tossed two coins a bunch of times. What's going to happen? Definitely not going to be an exactly 100. So that is absolutely not true. The odds against two heads are 4-1. It's actually the odds four heads are 2-1, and we're 4-1. We're not going to be using those words too much. In the long run, the average number of heads is 0.25. Actually, the average is not 0.25. The average times you get two heads is 0.25. In fact, the average number of heads when you flip two coins over the long run is one, actually, because you'll get one heads, one tails. Um, or two heads, two tails. And in the end, it will even out. In the long run, heads will occur in 25% of all tosses. Beautiful, easy peasy. And just to read the last one here, if you get two heads on each of the first five tosses, you are unlikely to get heads the fourth time. This is nonsense. Every coin flip is independent. Definitely useless. Let's go on to number two. You are playing a board game with some friends that involve rolling two six-sided dice for 8 consecutive rolls. The sum of the dice is 6. Which of the following statements is true? So if this happens, in real life, it's actually something that definitely could occur. It's just extraordinarily unlikely to occur. So that's what we're looking for. Probably rolling a ninth roll is the same as it was in the first roll. D, that is exactly what we're looking for on this one. The idea that when you roll, the probability of one thing happening goes up or down is nonsense. It's actually how casinos will trick you. They'll have things like a roulette table where they have all the numbers shown, and it's like, oh, the red numbers came 10 times in a row, so a black number is going to come next time. And this is just nonsense. It's not going to happen this way. We don't want to worry about it. These are independent. However, I do have to say, if you have actually rolled the dice 8 times in a row and got a 6 all the times, this answer is reasonable. Actually, you should find another set of dice. I wouldn't even be that bad with that answer at the start. However, the word "not possible" is what makes it wrong. It is possible. It's just very, very unlikely. However, if this did happen in real life, I would definitely look at the dice and see maybe if it's weighted on one side or the other. You never know. The collection of all possible outcomes of a random phenomenon is called the sample space, just as a definition. We just got to know that one. So I guess we got the letter D 3 times in a row. What do you know? All right, let's read question number 4. Miss Lee selects 2 cards from a deck of 52 cards and observes the color of each. 26 cards in the deck, 26 red, 26 black. Which of the following is the appropriate sample space of possible outcomes? So you're selecting 2 cards, so it's either going to be red, red, black, black, red, black, or black, red. So let's see, that's what we want. So we have red, 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 black, black, red, black, black. That looks good. This one's missing the black, red. So we're going to go with letter B. Letter B is the sample space. Every single one of these going to be good. Finally, one that's not letter D is the answer. All right, let's go on to this next page. So our next page is problem number 5. So we have a hat holds a large number of slips of paper, each with a digit from 1 to 4 on it. Which of the following is a possible probability distribution for the number on a single randomly selected piece of paper? So single digit from 1 to 4. So we need to have 1, 2, 3, 4 represented. And then all of these numbers, the total, the sum has to be equal to 1. It has to add up to 100% no matter what. So right away, looking at this one right here, we know that A is not correct because it has a 0. B is not correct because it has a 0. So we're really looking at letters C, D, and E. E is nonsense because you can't have negative probabilities. The lowest a probability can be is 1. So now it's between these ones. So which ones of these is going to add to a total of 1? So if we did 0.25 plus 0.15, just added these up, plus point, if I added all these up, what's that going to be? It's like, so this is those total to 0.7. So because they total to 0.7, this is not going to be good. It needs to total to 1. So it's got to be this letter D. But just to prove to ourselves that this is a true statement, we need to double check that 0.05 plus 0.15 plus 0.50 plus 0.30. That sure enough does actually add up to 1.00. And you can't even see the work for it because I'm over here with my face blocking the entire thing. I apologize for that earlier in the question. I think I slid it down. Actually, you could have seen it earlier, but then I slid it back up, and well, life goes on. Okay, we're moving on to the next question. A die is loaded, so the number 6 comes up 3 times as often as every other number. What is the probability of rolling a 1 or a 6? I think this is a great problem to actually write down all the different possibilities. So basically, you can get a 1, a 2, a 3, a 4, a 5, a 6, but the 6 comes up 3 times as often as all the other numbers. So we're going to go ahead and write, another 6, another 6. So that is basically all the things that show up. Those are 3 times as often as the other numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8 different options now. So our probability of rolling a 1 or a 6, the probability of 1 or 6, these are going to be what are called mutually exclusive. So because it's mutually exclusive, probability of 1 plus the probability of 6. And then this is done because mutually exclusive means that the probability of the and is 0. So if I said 1 and 6, this part here is 0 because they cannot happen at the same time. 0 because we're going to say mutually exclusive. It's a good definition to know. Exclusive. Holy moly, you can't even read my handwriting. All right, so we got 0 there, so that's going to be gone. Probability 1 plus probability of 6. Well, there's 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be a 1 out of 8 times, but these come up 3 out of 8 times. And if you add those together, you get 4 out of 8, which reduces to 1/2. So I think that's one way of doing it. There are other approaches to doing this question, but I think this is probably going to be the easiest. There's a more algebraic approach to it where you would say like that we know that every single one of these has a probability x, right? So all of these have a probability of x because they all will occur as often, except for the number 6. Effectively, you're going to write it as a 3x for that one because it shows up 3 times as often as the other ones. But if you add up all the x's, you get 8x. So I don't know. This is another way of approaching it if you really wanted to do it, and you'd figure out that each one of these is 0.125. I'm done talking. I'm moving on to the next idea. All right, ignoring twins and other multiple births, assume that babies born in a hospital are independent random events. The probability that the baby is a boy and probability the baby is a girl is equal to 0.25. What is the probability that the next 5 babies are girls? So every single baby has to be a girl. We're going to use our independence rule for multiplication. That is to say 0.5, and then we're going to multiply it a total of 5 times. So 0.5, 0.5, 0.5, 0.5, 0.5, or a better way of typing it into our calculator, 0.5 to the 5th power, and we're just going to figure out what is 0.5 to the 5th power. So we got 0.5 and raise it to the 5th power. Turns out to be 0.03125. So there you go. Another way of looking at this question, by the way, you could say something like if you're going to have like 100 families that had 5 kids, out of those 100 families, you'd probably have about 3 families with all girls and about 3 families with all boys. So just kind of interesting. If you were having that many kids, there is a non-zero chance for sure of those things happening. All right, let's move on to the next page. All right, so we are having a question here about Miss Levy. Miss Levy asked 100 high school students if they had a dog, a cat, or both at home. Here are the results. If 2 students are selected at random with replacement, what is the probability that neither of them has a dog or a cat? So basically, because you have this with replacement, so you could end up selecting the same student twice, the probability of these kids having neither dog or cat to know is right here. That's 74. So it is a 74 out of 100 chance because of that total over there. So the probability of them having neither of them is going to be 74 over 100, but it's going to happen 2 times. So it's 74 over 100 twice. You could also just do, in my opinion, the faster way of typing this one would be 0.74 all squared. That would be the faster way of doing it. So we got 0.74 squared, and it turns out to be 0.5476. And there we go. Looks like that's letter C. I'm like, oh no, the answer's not there. What a disaster. All right, we're okay though. Let's go to the next one. The two-way table gives these Information on seniors and juniors at a high school by which they typically get to school. You select one student from this group at random. What is the probability that this student typically takes a bus to school? So you're asking from this entire group, probability of bus. So bus is this column. That's the number of bus. That's the total. So we're looking at 170 divided by 550. 170 divided by 550. We got this equal to 0.30909. Whatever that's going to be, looks like that is an answer immediately. Letter B. Let's check out the next one. Event A occurs with probability 0.2. Event B occurs with probability 0.8. If A and B are mutually exclusive, disjoint, they never occur at the same time, then the probability of A or B is equal to 1. The reason why is just that same exact formula we had before in the previous page, where the probability of A or B is always equal to the probability of A plus the probability of B minus the probability of A and B. So probability of A plus probability of B is what your probability of A or, so we're going to have that 0.2 plus 0.8, but again, this is 0 because if they are mutually exclusive, they can never occur at the same time. So definitely going to be the letter A or B is equal to 1.0. Letter A. Guess I should have double checked A and B are true. It's not true, but they could have been. All right, post A and B are independent events. So now we're doing the same exact thing as the previous question. We're using that same exact formula. So I'm going to write it again. It's the same exact formula. Remember that this little guy here, this little union symbol is the same as the word or. So we're doing the same exact thing, except now they're independent events. So when they're independent events, we're still going to have that same exact idea of, it looks like 0.2 plus this one's going to be 0.4. But now, when we subtract the A and B, the independent events rule is the same anytime you have independent events. Probability of A and B at the same time is the probability of A multiplied by the probability of B. And that is true for independent only. Independent only. You can only do this for independent. Probability of A and B is these two multiplied together. So 0.2 multiplied by 0.4. Put in parentheses if you want to. I'm just going to put all of it into the calculator at the same time. 0.2 plus 0.4 minus, and then 0.2 times 0.4. You actually don't need those parentheses, but I put them in there because it makes me happy. 0.52. Letter D. Easy peasy, moving on with my life. Number 12, Mrs. Auld, about this cats and dogs again. So we have dogs and cats. Looks at the same table, different teacher, get the same results. What are the odds of that? If a single student is selected at random, what is the probability associated with the union of events has a dog? What is associated with the union of the events has a dog and does not have a cat? That is a really terribly worded question because the word union means or, but it says the word and over here. I'm going to go with the word or. So this word union is going to be or. And because of that, that's what I'm going for here. So what is the probability of has a dog? So has a dog is going to be the number 10. So dog, yes. This is the yes dog column. And then does not have a cat. So does not have a cat is this row over here. And it wants to know the union of them. The easiest way to do this question is to simply select each one of those exactly once where it occurs. You do not need the edges. You do not need, by the way, those are called marginal distributions. You don't need the marginal distribution. So we're going to add this number and this number and this number, and we're going to be putting them over 100. So that's going to be our final answer. We're going to do 74 over 100 plus 4 over 100 plus 12 over 100, and that's going to end up equaling 78 and 12 is 90 over 100, which is 0.9. So that is, in my opinion, the easiest way of doing this question. However, if you'd like to use it from the whole union idea, is you could use that same formula we did on the previous page. So we did the same formula on the previous page. It'd be the probability of has a dog, so dog, plus probability of does not have a cat, so we'll do cat with a bar over it, minus the probability of dog and no cat. So, or maybe an intersection symbol instead, right? Okay, if you did it this way, the probability of a dog would be 84 over, oh, not, I lied to you. I lied to you. Probability of a dog is right here, is 16 over 100, because you're doing the entire 16 column. The not cat is 78, so no cat is 78 over 100, and then the cat and dog at the same time, or dog and no cat, sorry, is 4 over 100, and if you add this up, you can check 16 plus 78, that is 94, minus 4 also gives you the 90 over 100. So you could do this problem two different ways. I really think when you have these tables, though, you should just like pick the ones there that's a little bit easier to do. All right. You ask a sample of 370 people, should clinical trials on issues such as heart attacks that affect both sexes use subjects of just one sex? The responses in the table below. Suppose you choose one of these people at random. What was the probability the person said yes, given that she is a woman? So probability of yes, given that you are I put girl instead of woman. I don't, whatever. My brain. All right, so probability of a yes. I'm going to rewrite it one more time because this is an official video. My goodness, Mr. Richards. All right, probability of a yes, given that you are a woman. If you're going to be doing it this way, when you use our conditional probability rule, our conditional probability rule says that you treat this bar kind of like a fraction. So we want the probability of women on the bottom and the probability of Y and W on the top. So probability of a woman, period. How many females are there? So how many females in this are there? We have 46 and 185. So we're going to add those numbers up. I don't know why I'm using a calculator, but I'm officially nervous about getting this wrong after I wrote number down. So I got 231 on the bottom. And the probability of yes and woman, well, the yes and woman's right there is the 46. So it's whatever this number happens to be. 46 divided by 231. And that is going to be 0.199. So is that an answer? I suppose they want us to select 0.2 because it rounds up. There it is. There it is. The other way of approaching this question, by the way, is to add these up first, 231, and then realize that you can ignore the male row completely and then just do 46 over 231 because you're only looking at the female row. Woof! All right. I need to like wake back up, but it's not going to happen. Here we go. Ignoring twins and other multiple births. We have the same exact type of question. The events A is the next two babies are boys, and B, the next two babies are girls, are what? Mutually exclusive, conditional, independent, complementary, or E, none of the above. So complementary means that they are opposites of each other, and maybe they are opposites of each other in the English language sense, but they are absolutely not opposites of each other in this sense, because the opposite of the next two babies are boys is that the next two babies are not both boys. So you could still have one boy, one girl, would be part of the complement of A. Either way, these are mutually exclusive events. You can't have both two babies that are boys and two babies that are girls at the same time. So there we go. We're gonna go ahead and say mutually exclusive. That's our definition. All right. Number 15, a stack of 4 cards contains 2 red cards and 2 black cards. I select 2 cards, one at a time, and do not replace the first card selected before selecting the second card. Consider the events A, the first card selected is red. B, the second card selected is red. The events A and B are independent and mutually exclusive. No, absolutely not. So first of all, they are not independent. They are dependent, because if you draw a red card first, or if you draw a black card first, the probability of drawing a red card or black card changes. So no matter what, the second card, the probability of the second card depends on the first card. So they are absolutely not independent. They are dependent on each other. So they are, because they are independent, we have to figure out what it is. So the first card selected is red, and the second card selected is red. They are also not mutually exclusive because they are able to happen at the same time. You can draw 2 red cards in a row, so they are not independent, nor are they mutually exclusive. Not going to happen either way on this particular question. So I wonder. I'm gonna pause the video really quick. All right, so we're back. It's was not paused for you, paused for me. All right, I was just checking to see if I'd gotten all the right answers yet. I didn't want to make a mistake. I was nervous about it. I don't know why I was nervous. They were all right. All right, number 16. Which of the following statements is not true? So we're looking for a not true statement. Here we go. Letter A. If two events are mutually exclusive, they are not independent. Okay. Which one? If two is not true. So we're looking for which one is not true. All right. So if two events are mutually exclusive, they are not. I need to pause. Okay, I was tongue twisting myself. All right. If two events are mutually exclusive, they are not independent. This is actually a true statement. In the event that two things are mutually exclusive, they are guaranteed to be dependent on each other. They are not independent because mutually exclusive means they cannot happen at the same time. So if one of them happens, then the other one has a probability of 0. So so that's another way of thinking about it. Let's write this down. Mutually exclusive. What that means is, again, is that the probability of A and B, the probability of A intersection B, is equal to 0. They can never occur at the same time. Or in other words, another way of writing this is to say that if A occurred, if A happens, B doesn't. And vice versa, by the way. If B happens, A doesn't. So that's what mutually exclusive means. So because if A happens, then B doesn't, then they're not independent of each other. So this is definitely a true statement. All right. If two events are mutually exclusive, then the probability of them, we just wrote that down. If two events are independent, then they must be mutually exclusive. If two events are independent, so now we're looking at the other way around. They're independent. Then they must not be mutually exclusive. It's the other way around. Wait. Sorry, maybe not. If two events are independent, so that means that so that's not true. Then they must not be mutually. Yeah, it's the other way around. They must not be mutually exclusive. So letter C must be the correct answer. Let's double check the last one. If two events A and B are independent, the probability of A is the same as probability of A given that B has occurred. That's a definition. So we're good to go. Must be letter C as our correct answer. All right, number 17, Coach Kemp chooses a student at random from Coppell High School student body, and the following events are recorded. M, student is male, F, student female, B, student ate breakfast this morning, and N, student did not eat breakfast this morning. Here we go. Following probability diagram. So remember that whenever you're looking at tree diagrams, each one of these is a conditional probability based upon the previous results. So we're looking at what's the probability a selected student is male and ate breakfast. So both of those things, this is going to be an easy one. Anytime you're looking at an and on a tree, you just multiply that line. So male is here, breakfast is here. So we're looking at 0.4 multiplied by 0.32. So whatever that happens to be, what is that? We got 12 and 16. I mean, it kind of, with, sorry, 12 and 8. Man, I can't speak. I'm going 0.4 times 0.32. There we go. You got 0.128. Uh-oh. What is the probability a student is male and ate breakfast? I did it correct, but that is not one of the answers. I am going to pause because I don't know what's going on. Holy Toledo. I multiplied these two together right away. My brain didn't even let me do it. It's 0.4 multiplied by 0.8. That's the answer to the question. I decided to multiply them first, then put it there. We're reaching the end of our days, guys. I don't know what's going on. I apologize for that question. We're moving on number 18. I'm not recording. I'm not gonna edit this thing. I need to learn how to edit videos so I can fix stuff like this. All right, ignoring twins and other multiple births and the babies that were the same exact thing. What is the probability that at least one of the next 3 babies is a boy? So one of the best ways of getting these at least one ideas is remembering that the probability of at least one no matter what it is that you're dealing with, as long as they're independent events, the probability of at least one is the same thing as 1 minus the probability of 0. That is always going to be the case. So really all you need to do is with the probability that 0 of them are boys, and the probability of 0 of them being boys is going to be the probability of all 3 of them being girls. So 0.5 to the third power, because there are 3 of these situations. So 1 minus the 0.25, I believe that's going to be 0.875, but I am officially in the going nuts mode, so I'm going to go up here and say, I'm using my calculator. Okay. There you go. Letter E, we're done. Big idea. And again, this is a big idea for in general, and we're going to use this a bunch later in the year. Okay. Two more. Number 19, if you buy one ticket in the provincial lottery, then the probability that you will win a prize is 0.11. Given the nature of lotteries, the probability of winning is independent from month to month. If you buy one ticket each month for 5 months, we'll probably win at least one prize. Exactly the same idea as that last one. We are looking at 1 minus the probability of never winning. Probability of 0 wins. So because the probability of winning a prize is 0.11, the probability of not winning a prize is so let's gotta figure out this. The probability of lose must be the same as 1 minus 0.11. So that's going to be 0.89. And we are now doing 0 wins, which is going to be 1 minus 0.89 raised to the 5th power. So that's what we're looking for. So the probability of simply at least one prize is 1 minus never happening, and we're doing that. So 1 minus, and we got 0.89 raised to that 5th power, and we got 0.4415. Beautiful. Pause it again. Okay, you play tennis regularly with a friend, and from past experience, you believe that the outcome of each match is independent. For any given match, you have a probability of 0.6 of winning, was probability to win the next 2 matches. This is kind of a freebie just to end it, 0.6 squared, because the probability is 0.6, and you multiply it by itself for any independent situation. You only got 2 of them. Freebie to end the assignment. All right, let's go on over here. Not the whole assignment, I mean the multiple choice section. Here we go. Which age groups use social networking sites? So we're looking at the 768 individuals in the age and the networking sites. People who did not use such sites were excluded from the study. We have Facebook, Twitter, and LinkedIn. I technically have a Twitter. I just never really use it. Facebook, Twitter, LinkedIn. I think I have a LinkedIn too. I get emails about it, so I must have one. I don't think I've updated that one since, I don't know, probably 2009. All right, so we have all of this stuff written in. Let's check out what the questions are. So the probability that a selected subject preferred Twitter. So if you preferred Twitter, that's going to be this Twitter row. So we got 244 divided by the overall total 768. And remember, you do not need to reduce. You do not need to turn these into decimals. However, it will be easier to use the decimals later if you do. If we need use this, so I'm going to quickly divide those two. Approximately 0.3177. There you go. Find the probability of the selected subject preferred Twitter, given that he or she was in the 45 to 64 age group. So just like we did before, anytime we're finding a given probability, when you're looking at these given probabilities, you're going to want to either use the formula or use the column method. So I did the formula last time. I'm going to use the column or row method this time. So 45 to 64 age group. 45 to 64 age group is this one here. I'm only looking at this one for letter B. So for letter B, I'm only looking there, which means my denominator for this entire thing, my total out of all of them is 290, because that's the only section I'm looking at. And then you're finding the probability that they preferred Twitter. So it looks like there's 81 there. So 81 over the 290. And again, if we need this later, I will decimalize it just because 81 divided by that 290, and we have 0.2793. Okay, letter C, are the events preferred Twitter and age groups 45 to 64 independent? So in order for them to be independent, 2 things have to be true. So in order for them to have to be true, we have to know that the probability of A is the same thing as the probability of A given that B has already occurred, and also that the probability of B has to be the same as the probability of B given that A has occurred. If both of those things are true, then we have independence. So we need to check both of them. So checking both of them, let's go ahead and do that. So checking this first one, the probability of A, first of all, preferring Twitter. This is what I was talking about earlier. We need this number before, so we already did that. We have 0.3177, but the probability of A given that B has already occurred, what are we going to do for that one? So now we're looking at age group 45 to 65. Well, that's the one we already did here. We figured out that that is 0.2793. Are those two numbers the same? Absolutely not. So no. In terms of the actual explanation, this is actually enough because you showed these two things are not equal to each other. You are done doing independence. If you'd like to have a nice sentence, you could say something to the effect of, because the probability of Twitter is not equal to the probability of Twitter given that you are in the age group 45 to 65, then these two events must be dependent on each other. Letter D. Are the events preferred Twitter and the age group 45 to 64 mutually exclusive? That would mean that would never occur at the same time. So what we have to do is we need to look at the and section of this. So we're looking for Twitter and 45 to 64. Was there anybody in the and section? Yes, there was at least one person. So no, and we would just say the probability of, I don't know, Twitter and 45 to 64, what that number is it, well, it's not 0, right? Because it's not 0, that's a no. All right. If a random sample of two subjects were selected, was a probability that neither preferred Twitter. So this is kind of interesting because we need two different people, and we want the probability that neither of them preferred Twitter. So which ones do not prefer Twitter? There's going to be so I'm just going to look at this column over here, looking at these numbers right over here. So we're going to be looking at not preferring Twitter is going to be 308 plus 216. So that's the total there, and you're going to be dividing that by 768. So that's the probability of the very first one, not preferring Twitter. Let's go ahead and add those up. 308. Uh-oh. My calculator right? No. 308 plus 216. That is 524 divided by 768 divided by 768. And this happens to be 0.68229, so 6.8223. Okay. And now if two of these subjects were selected, was a probability that neither preferred Twitter, but it doesn't say that it was like selected with replacement. So that means that once you've selected one of these people, now there's only 523 left in the group, and also only 767 left in the group. So this number, if we divided both of those separately, we got 523 divided by 767, and this is going to be 0.6818. So you can see it's really, really similar numbers, and if you only rounded the two decimal places, they're actually exactly the same thing. This is one of those things that's going to be common later in statistics. If you have a large enough number and you don't round, and you round early, then you get almost the same answers. I'm not too stressed about it one way or the other. However, I will say, if you're going to be doing this on the test, make sure you're not multiplying these rounded numbers. Multiply the original fractions. And to do that, we're going to go ahead and highlight the answer we got from before, and then we're going to multiply it by the answer we had second, and we are going to end up getting 0.4652. And that is going to be our final answer. We multiplied those two numbers together. In addition, one other thing I would say is if you actually just use the original number twice, so let's just see what happens if we use the original number twice, and then we squared it, we'd actually end up with almost an identical answer. And in fact, we'd only be off at the fourth decimal place. And many times, if you'd like skip some steps or something and written your final answer, you would have just been fine anyways, because you would have gotten the same thing, and they're not going to do that to you in the test. So anyways, I'm done talking. Have a great rest of your day. Peace out, guys.